Hello. In this lesson we will discuss heat capacities of gases. Tell me first of all, what is the meaning of heat capacity? We discussed the difference between specific heat and heat capacity. Well, heat capacity is mass multiplied by specific heat. In other words, it's a measure of the amount of heat required to raise the temperature of a given amount of substance by 1 Kelvin. So, in this lesson we will discuss heat capacities of gases. When you talk about gases, there is a little problem. The problem is the amount of heat required to raise the temperature of a given amount of gas by 1 Kelvin depends on whether the gas is kept at constant pressure or constant volume. The two quantities of heat are different. Therefore, we have two types of heat capacities for gases. We will talk about these two types of heat capacities in this lesson. Heat capacity of a substance is a measure of the amount of heat needed to raise the temperature of the substance by 1 Kelvin. And we can represent C as mass of the substance divided multiplied by specific heat, which is m times small c. We know that, we have used that earlier. If a quantity of heat dq added to a substance increases the temperature by dt, then dq equal to c dt. Do you understand that? If C is the amount of heat needed to raise the temperature by 1 Kelvin. So if you want to increase the temperature by an amount dt, the total amount of heat you need is C times dt, where C is the heat capacity. What's the heat capacity? It's a measure of the amount of heat needed to raise the temperature of the whole object by 1 Kelvin. So if you want to raise the temperature by a quantity dt, the quantity of heat you require is C times dt, heat capacity times dt. Or we can write this as C, the heat capacity, is dq over dt. Now actually, this is a better definition of heat capacity, isn't it? The amount of heat required per Kelvin rise of temperature, dq by dt, the rate at which heat is used in raising the temperature. That is the definition of heat capacity. Alright, so keep this. C equal to dq by dt, the amount of heat needed to raise the temperature by 1 Kelvin. The amount of heat needed to raise the temperature of a given mass of gas by 1 Kelvin depends on whether the gas is kept at constant volume or if it is kept at constant pressure. As I have told you earlier, these two quantities are different. Therefore, we have to define two types of heat capacities for a gas. What are they? The first type is when you keep the gas at a constant volume. And the second type is when you keep the gas at a constant pressure. Well, let's take the constant pressure first. Heat capacity of a gas at constant pressure is represented by Cp, C sub P. It stands for heat capacity at constant pressure. In the same way, the heat capacity of a gas at constant volume will then be C sub V. So Cp stands for heat capacity at constant pressure, and Cv stands for heat capacity at constant volume. Let's now consider heat capacity at constant volume. The amount of heat required to raise the temperature of a given amount of gas by 1 Kelvin when the gas is kept at constant volume. That is what we need to find. When a gas is kept at a constant volume, you know that when the volume doesn't change, there will be no work done. That means all the amount of heat you supply at constant volume will be used in raising the internal energy. If you remember, the amount of heat you supply to a gas will be used in increasing the internal energy and also doing work. Since when the gas is at constant volume, there is no work done. Therefore, all the heat that you supply to the gas at constant volume goes into increasing the internal energy. Therefore, we can say when the gas is at constant volume, dQ equal to du. And therefore, what is the definition of heat capacity at constant volume? It will be dQ over dt. That is the basic definition of heat capacity. dQ over dt. Therefore, dQ over dt is the same as du over dt. So, heat capacity at constant volume is a measure of the increase in internal energy per Kelvin rise in temperature. Isn't that interesting? The increase in internal energy per Kelvin rise in temperature. But dQ over dt is the heat capacity. Therefore, the heat capacity equal to du over dt. Cv, the heat capacity at constant volume, equal to du by dt, where what does du stands for? Du is the change in internal energy. Alright, I want to go back and ask you the same question I have been asking you several times. What is the internal energy of n moles of a gas? Do you remember that equation? The internal energy of n mole of a gas is 3 over 2 nRT. Is that right? Okay, we will talk about that as we go on. Now, before we talk about it, let's now discuss heat capacity at constant pressure. When a gas is heated at constant pressure, it expands. It expands means it does work, and in addition to doing work, its internal energy rises as well. So both these things happen when you supply heat to a certain amount of gas at constant pressure. Its volume increases, it means it will do work, and the internal energy increases, that means there is a change in the internal energy. So dQ equal to du plus dW. And what is the definition of heat capacity? Heat capacity is dQ over dt, right? Now, you know that Cv equal to du over dt, is that right? That's what we just found out earlier. So Cv equal to du by dt, therefore I can replace this du by what quantity? Du equal to Cv dt, is that right? So I'm going to say du equal to therefore Cv dt, and dW, I'm recalling all the things that we did earlier. Didn't we do this earlier on in the last lesson, that the work done is PdV? So using those two together, I can write dQ equal to du I replace by Cv dt, and dW, the work done, is PdV. And of course, remember, P is a constant here. Well, divide by dt. Why do you want to divide by dt? Because we are looking for dq by dt. dq by dt is the heat capacity at, well, this dq by dt is a measure of the heat capacity, whether it is at constant volume or at constant pressure. So in this case, when dq equal to du plus dw, where du is cv dt and dw is pdv, in this case dq by dt will be our Cp. So dq by dt equal to, I'm dividing each term by dt. So the left hand side is dq by dt. Cv dt divided by dt will be Cv, plus pdv divided by dt will be pdv over dt. Well, what's our next step? dq by dt is our Cp. So you have Cp equal to Cv plus pdv. Now, is it possible to replace this pdv by a more friendly term? Where do we go for that? Well, we go to our familiar equation. What is our familiar equation? The ideal gas equation. PV equal to nRT. All right, let's go there. We now find dV by dt using the relation PV equal to nRT. Well, P is a constant. So, if you find the derivative of left-hand side and right-hand side with respect to t, what will you get? Take the differential of both sides. What is the differential? The differential of V will be dV. The differential of t will be dt. Here, V and t are the variables. P is a constant. nR also is a constant. So, if you take the differential of both sides, we will get P times dV equal to nR times dt. There you are. P dV equal to nR times dt. And now if you divide both sides by dt, I can now produce P dV by dt. Divide both sides by dt, we get P dV over dt equal to nR. Well, you could have actually obtained the same relation from here, finding the derivative of V with respect to t. You see that? You can also do that rather than going through the differential path. Okay, P dV by dt equal to nR. That means I can replace this P dV by dt equal to nR. So what does Cp equal to? Cp equal to Cv plus nR. That's a beautiful relation. The heat capacity at constant pressure equal to heat capacity at constant volume plus nR, where n is the number of moles of the gas and R is of course the universal gas constant. Now, so which of these is greater, Cp or Cv? Cp is definitely greater. Why? Why is Cp greater? Because when you supply heat to an amount of gas at constant pressure, that amount of heat is used in two ways. One, to increase the internal energy, and two, to do work. Whereas, when you supply heat at constant volume, there is no work done. Therefore, the amount of heat you supply at constant pressure is greater than the amount of heat you supply at constant volume. Cp is greater than Cv. By how much? By a quantity equal to nR, where n is the number of moles of the gas. Therefore, what is Cp minus Cv equal to? Cp minus Cv will be equal to Nr. The difference between heat capacity at constant pressure and heat capacity at constant volume is Nr. Remember that. Cp minus Cv equal to Nr. Okay. This question I must have asked you by now at least a half a dozen times. What is the internal energy U of n moles of a gas? Even I asked you this about 10 minutes ago. What is the internal energy U of n moles of a gas? Well, internal energy U equal to 3 over 2 nRT. Okay. Now, take the derivative of U with respect to T. If you take the derivative of U with respect to T, you get du over dt on the left side. Can you tell me what is du over dt? What is du over dt? Is Cv, the heat capacity at constant volume, and that's why we are doing this. Alright, we get du over dt is 3 over 2 nr is a constant, and the derivative of t with respect to t is 1. So du by dt equal to 3 over 2 nr. Now this is a very important relation. Why? Because du by dt is the heat capacity at constant volume. And what does it tell you? The heat capacity of a gas at constant volume is 3 over 2 nr. Alright, so Cv equal to 3 over 2 nr. Now, I want you to be using a caution here. And the caution is, where did we get this relation? The internal energy of n moles of a gas is 3 over 2 nRT. Now, is it obtained from any established laws? No. We obtained this from kinetic theory of gases based on our assumptions. We used 4 assumptions and we arrived at this conclusion. We arrived at this conclusion based on those 4 assumptions. Therefore, we don't know whether this is a true statement or not. But this is an opportunity for us to test, because heat capacity of a gas at constant volume and constant pressure can be measured in the lab very accurately. So, I can now take n moles of a gas and measure its heat capacity at constant volume and see if it will give me 3 over 2 nr. If it gives me 3 over 2 nr as the experimental value, then I can say, yes, the assumptions we made were right. On the other hand, if the measured value does not give you 3 over 2 nr, then we can say we made a mistake. Our assumptions were not right. See, look at the way science operates. Alright, let's go and have a look at this. So, Cp, we got Cv equal to 3 over 2 nr, and you remember in the last slide we had this relation, Cp equal to Cv plus nr. And if I now replace this Cv by 3 over 2 nr, I can now get Cp equal to 3 over 2 nr plus nr. And what does that equal to? That will be 5 over 2 nr. That means if Cv equal to 3 over 2 nr, then Cp must be equal to 5 over 2 nr. Because the difference between Cp and Cv is simply an nr. So if Cv equal to 3 over 2 nr, then Cp must be equal to 5 over 2 nr. Now the question is, Are these relations right? Now, how do we know? Well, we can actually go and look at measured values of heat capacities. Do we have measured values? Well, we have, but before we go to that, let me introduce you to this concept. What is molar heat capacity? Well, heat capacity is a measure of the amount of heat needed to raise the temperature of the whole amount of gas. And the amount of gas consists of n moles of the gas. So, Cv is the heat capacity of n moles of a gas. Cp is the heat capacity at constant pressure of n moles of a gas. What is molar heat capacity? Molar heat capacity is the amount of heat needed to raise the temperature of 1 mole of a given gas at constant volume. They increase the temperature by 1 Kelvin, and that will be the molar heat capacity at constant volume. So once again, molar heat capacity is the amount of heat needed to raise the temperature of 1 mole of a gas by 1 Kelvin. And if the gas is kept at constant volume, it will then be the molar heat capacity at constant volume. And if the gas is kept at constant pressure, it will be the molar heat capacity at constant pressure. Now tell me, if you look at this relation, you will be able to answer my question. What does Cv stands for? Cv stands for the amount of heat needed to raise the temperature of n moles of a gas at constant volume by 1 Kelvin. And therefore, what will be the molar heat capacity at constant volume? But all we need to do is divide that quantity by n. Is that right? Because this is the amount of heat needed for n moles of a gas. Molar heat capacity is the amount of heat per mole. So divide by n, you will get the molar heat capacity at constant volume is 3/2R. Alright, let's write these things down. Now, molar heat capacity is measured in joules per mole per Kelvin. You see, once you know the unit, you know the definition. You can see, molar heat capacity is the amount of heat in joules needed to raise the temperature of 1 mole of a gas by 1 Kelvin. Joules per mole per Kelvin. Now, Cmp, now we're going to represent the heat capacity, the molar heat capacity at constant pressure, we will represent by Cmp, and the molar heat capacity at constant volume we will represent by Cmv. So let's see what Cmp is. I want you to look at this again and think about it. Cp is the amount of heat needed to raise the temperature of n moles of a gas at constant pressure by 1 Kelvin. Therefore, the amount of heat needed to raise the temperature of 1 mole, you divide by n. In other words, Cp divided by n is Cmp. Cmp equal to Cp divided by n, and Cp equal to 5/2 nr. So what do you get if you divide 5/2 nr by n? You get 5/2r. And look at this, the molar heat capacity for at constant pressure of any gas is 5/2r. Now what is the significance of it? R is the universal gas constant. It means the molar heat capacity at constant pressure for any gas should give you the same value, 5/2R. In the same way, CMV, what does CMV stands for? Molar heat capacity at constant volume, will be equal to CV divided by N, the amount of heat per mole. And if you divide this quantity by N, you get 3/2R. So, molar heat capacity at constant pressure is 5/2R, and molar heat capacity at constant volume is 3/2R. That means the difference between CMP minus CMV is 5/2R minus 3/2R, which is an R. The difference between molar heat capacity at constant pressure and molar heat capacity at constant volume must be equal to R. Now the question is this true? Are we going to get that right? CMP minus CMV must be equal to R. Now this means that molar heat capacities have constant values for all gases. There is no difference between the values of CMP and CMV for any gas. They all will have the same value. And what will be that value? CMP, the heat capacity, molar heat capacity at constant pressure is 5/2R, which is 2.5R. That will be 2.5 times 8.314. That will be 20.79 joules per mole per Kelvin. This is the value of CMP. Now, this is the theoretical value. What is the meaning of that? Well, assuming that our assumption is right. All these are based on our assumptions. You see, these results are based on the assumptions we made in kinetic theory. So if our assumptions are right, then the value of CMP for all gases must have a value 20.79, and the value of CMV for all gases must be 3/2R, which is 1.5R, or 12.47 joules per mole Kelvin. Well, one consolation is we can check it very easily, because these quantities can be measured experimentally. Now look at this. Measured values of CMP and CMV shows that for monoatomic gas, this prediction is true, while it fails for diatomic and polyatomic gases. So, are we all right, or do we have a problem? Well, we have a problem. What is the problem? Experiment, I'm going to give you a table of values. So remember these values. We would expect that the molar heat capacity at constant pressure for all gas to be 20.79, in the neighborhood of that, and the molar heat capacity for all at constant volume for all gases to be in the neighborhood of 12.47. Now look at the measured values. If you notice that heat capacity at constant pressure for helium, neon, argon, krypton, xenon, they all agree. There you are. And the heat capacity at constant volume also agree. And look at this, CMP minus CMV must be equal to approximately R, and this is a good agreement. But come to diatomic molecule, nitrogen, hydrogen, oxygen, there is a big difference between the measured experimental values and the theoretical values. The theoretical values suggest that all gases must have this as the heat capacity, molar heat capacity at constant pressure, and all gases must have this value as the molar heat capacity at constant volume. Well, experimental measurement shows that it is true for monoatomic gases, but not true for diatomic and polyatomic gases. Where have we gone wrong? Where have we gone wrong? Well, I can tell you where we have gone wrong. Now, you remember in obtaining the internal energy of a gas as 3/2 nKT, or the energy per molecule. If you remember, we started here. The energy per molecule is 3/2 kT. Now, we said the energy for X motion is 1/2 kT. The energy for Y motion is 1/2 kT. And the energy for the Z motion is 1/2 kT. I hope you remember the concept of degree of freedom that I introduced. You see, in the lesson on kinetic theory, what we obtained is that energy of a molecule per degree of freedom is 1/2 kT. And we said a molecule has 3 degrees of freedom. You see, it can move in the X direction, Y direction, and Z direction. And therefore, the total energy of a molecule is 3 times 1/2 kT, which is 3/2 kT. Well, this assumption is true for monoatomic gases. You see, our experimental measurements agrees well with the results for the monoatomic gases. That means a monoatomic gas. What's a monoatomic gas? Well, each molecule or each atom exists on its own. That means they are not coupled with any other atoms. So this is a single atom, and each single atom has 3 degrees of freedom. That's fine. But in the case of a diatomic gas, look at this. A hydrogen molecule exists like this. That means in addition to their X, Y, and Z motion, these molecules can actually rotate about 2 different axes. They can rotate. So that introduces another degree of freedom. Because they can rotate about 2 axes, it introduces 2 additional degrees of freedom. Now look at the way we go and revisit our theory and make corrections to our assumptions that we made earlier. So, what is the correction now we have to apply here? It is not a very small correction. We will explain this discrepancy using the equipartition theorem. What is it? In the lesson on kinetic theory of gases, you saw that the energy associated with motion of a molecule in the X direction is 1/2 kT. The ability of a molecule to move in the X, Y, and Z directions are called degrees of freedom. A molecule consisting of just one atom, called a monatomic molecule, has the freedom to move in the X, Y, or Z directions. In other words, a monatomic molecule has 3 degrees of freedom, X, Y, and Z. Alright, the energy associated with each degree of freedom we obtained again in the class on kinetic theory as 1/2 kT. Therefore, the total energy of a monoatomic molecule is 3/2 kT. And that is what we based our theory on specific heat on. If a monatomic gas consists of n moles, each mole containing Na molecules, the total number of molecules will be number of moles times the number of molecules per mole. We have seen that earlier. So the total internal energy U of n moles of this gas is U equal to 3 over 2 n NaKT. And do you remember? Na times K is what we call the universal gas constant, equal to 3 over 2 nRT. And this is what we concluded earlier on, which apparently is quite right for this kind of gases. Now, this is consistent with experimental results. All right. A diatomic molecule, on the other hand, is made up of two atoms, and the combination, in addition to their X, Y, and Z motion, can rotate about two axes other than the axis containing the line joining the two atoms. Now, here is a diatomic molecule. Now, this molecule, in addition to the X, Y, and Z motion, that molecule can vibrate, well, can rotate. Now, it cannot rotate, if this is the diatomic molecule, it cannot rotate about this axis, but it can rotate about an axis of right angles. Look at that. It can rotate like this, it can rotate like this. So, a diatomic molecules, now you got assigned 2 additional degree of freedom. Now, this adds 2 additional degree of freedom to a diatomic molecule, bringing the total number of degrees of freedom to 5. So, the number of degrees of freedom of a diatomic molecule is now 5. Now, what is the energy associated with each degree of freedom? Is 1/2 kT. Therefore, what is the total energy of a diatomic molecule? It will be 5 times 1/2 kT. Since the energy of a molecule per degree of freedom is 1/2 kT, the total energy of a diatomic molecule is 5 over 2 kT. Now, the internal energy of n moles of such a diatomic molecules will be, the total internal energy is 5 over 2 nRT. You see, look at the correction we are now applying. Now, earlier we said the internal energy of all gases is 3 over 2 nRT, because we assigned only 3 degrees of freedom to every gas. But now you know diatomic molecules have 5 degrees of freedom. Therefore, the internal energy of n moles of the gas is 5 over 2 nRT. And that will now change our heat capacity values. So, internal energy is 5 over 2 nRT. Therefore, for a diatomic gas, now tell me, what is du over dt equal to? Du over dt equal to, if you find the derivative of u with respect to t, we get du over dt equal to 5 over 2 nr. And, well, this is per mole, but if you divide this quantity by n, now, let me show that to you. Now, here, I will see the energy per mole, U over N, equal to 5 over 2 RT. And now, this is the internal energy per mole. If you now take the derivative of this quantity with respect to T, that will be CMV. So CMV equal to 5 over 2R. What was the value we had got earlier? Earlier we got 3 over 2R. But that is true for monoatomic gas. So you must distinguish. For a monoatomic gas, CMV is 3 over 2R. But for a diatomic gas, CMV is 5 over 2R. Okay. And that will be 20.788 joules per mole per Kelvin. And if you now look at the values for diatomic gas, CMV must be 5 over 2R. Now, do they agree? Yes, they agree absolutely. And how about CMP? CMP then will be 7 over 2R, and that must be equal to 29.103. So we didn't have to do a lot of big corrections. As soon as you figure out what we omitted, well, we are back in business again. So our theory is actually very, very good. These values agree fairly well with the measured values, and therefore our theoretical considerations are based on solid grounds now. Now, polyatomic gases. Now, this is beyond this class. They are much more complex. The degrees of freedom of polyatomic gases are much more complex. So we will ignore that. We will not consider. We will only take monoatomic gases and diatomic gases and leave polyatomic gases for anybody who wants to do higher classes in physics. Molar heat capacities of solids. Now, a solid consists of a regular array of atoms and are connected by intermolecular forces which can be approximated as spring connections, like this. This is what I have shown you what a solid is like. The molecules can vibrate about their mean positions. That means they behave as though each molecule is connected to its neighbor by spring connections like this. Now, these atoms, in addition to their translational motion in the x, y, and z directions, also vibrate in x, y, and z directions. That means each solid atoms have 6 degrees of freedom. So, thus an atom in a solid has 6 degrees of freedom. And what is the energy associated with each degree of freedom? Is 1/2 kT. We have said this now numerous times. I don't think you can forget. The energy associated with 1 degree of freedom is 1/2 kT. Therefore, the molar heat capacity of a solid is 3R. Well, this agrees well with experimental observations. That means all our theoretical considerations have been verified experimentally, and we are in good grounds. This relation is actually called Dulong-Petit law, that the molar heat capacity for all solids is 3 times R. Okay, let's do a problem. 1 mole of an ideal diatomic gas. See, when you look at diatomic gas, you must say CMP is 7 over 2R, CMV is 5 over 2R. Is heated at constant volume from 300 to 600 Kelvin. Find the increase in internal energy, the work done, and the heat added. Find the same quantities if this gas is heated from 300 to 600 Kelvin at constant pressure. Well, first we have the increase in internal energy. Remember, increase in internal energy is dU. And you know, dU by dt is what we call CV. So du equal to Cv times dt. For a diatomic gas, Cv equal to 5 over 2R, and dt is given to be 600 minus 300, and that is 300 Kelvin. So what is the increase in internal energy? du equal to 2.5 R. Cv is 2.5 R times dt. That will be 2.5 times 8.314 times 300, and that is 6,236 joules. What's our B part? Now, because the heat is added at constant volume, the work done dW equal to 0. So we found the increase in internal energy and the work done. Remember, when there is no change in volume, there is no work done. Now, the quantity of heat added, dQ equal to du plus dW. du is this 6,236 and dW is 0. Therefore, dQ is the same quantity, 6,236. Alright, find the same quantities if this gas is heated from 300 to 600 Kelvin at constant pressure. What is the difference? Since the change in temperature is the same, the change in internal energy remains the same. We don't need to go and calculate it again. The change in temperature is from 300 to 600. The internal energy is solely due to the change in temperature. So that will not change from the previous problem. Well, work done is given by, what is the work done when the pressure is a constant? Well, W is integral V1 to V2 of P dV, which when the pressure is a constant is P times V2 minus V1. Is that right? An isobaric process. The pressure is a constant in this case. And we have N equal to 1, PV equal to RT. And since P is a constant, we have PV1 equal to RT1. Is that right? Because PV equal to RT, PV1 equal to RT1, that is take 1, and PV2 equal to RT2. You understand these relations? Pressure is a constant. It changes from state 1 to state 2. You see? And we have PV1 equal to RT1 and PV2 equal to RT2. We are looking for PV2 minus PV1 is the work done. Can you obtain that from here? Well, P times V2 minus V1 equal to R times T2 minus T1. Did you understand that? Look at this. P times V2 minus V1 means PV2 minus PV1. PV2 minus PV1 is RT2 minus RT1. That's what we have here. R times T2 minus T1. Now, you know these quantities. W, the work done, equal to P times V2 minus V1, which is the same as R times T2 minus T1. And we know those quantities. R is 8.314 times T2 minus T1 is 300, and that is 2,494. And therefore, dQ, the heat added, dQ equal to du plus dW, and that will be 8,730 joules of heat. A very, very important type of problem. Let's do another one. 1 mole of a monoatomic ideal gas is initially at 273 Kelvin and 1 atmosphere of pressure. What is the initial internal energy? Find its final internal energy and the work done when 500 joules of heat are added at constant pressure. Find the same quantities when 500 joules of heat are added at constant volume. Alright, we got T1 equal to 273 Kelvin. P1 is 1 atmosphere, convert that to Pascal, 1.01 times 10 to the 5 Pascal. And N equal to 1. What do we need to find? We need to find the initial internal energy. And for a monoatomic gas, the internal energy is 3/2 nRT. Now what are the things that we have? Do we have the temperature? Yes. So that will be 3/2 is 1.5 times N is given 1 mole times R is 8.314 and the temperature is 273. So the internal energy of the gas at constant volume is 3,405 joules. Alright? Find its final internal energy and work done when 500 joules of heat are added at constant pressure. Alright? When heat is added at constant pressure, dq equal to Cp dt. Is that right? Because the definition of Cp is dq over dt. Now 500 equal to Cp for a monoatomic gas. Cp for a monoatomic gas is 5/2 R, which is 2.5 R times dt. And that will lead you to dt, the change in temperature. So we can now find the change in temperature dt. How? dt therefore, see 2.5 R dt is 20.79 dt. 2.5 times 8.13 is this. So 500 equal to 20.79 dt. Therefore dt equal to 500 divided by 20.79 and that is 24.05 Kelvin. Now the increase in internal energy is du equal to Cv dt. And that will be Cv is, for a monoatomic gas, Cv is 3/2 R multiplied by dt is 24.05 and using R equal to 8.314 we have that as 300 joules. The increase in internal energy is 300 joules. So the final internal energy is original internal energy plus the change in internal energy, and that is 3,705 joules is the final internal energy. I want you to practice these kind of problems. dq equal to du plus dw, and we need to find the work done. dw equal to dq minus du. That will be 500 minus 300 equal to 200 joules. Alright? C. Find the same quantities when 500 joules of heat are added at constant volume. The only difference is when heat is added at constant volume, there is no work done. Therefore, all the heat added goes into increasing the internal energy. Therefore, du equal to 500 joules and dw equal to 0. Okay, well, I want you to practice these kind of problems. I'm going to stop this part of the lesson here. I will come back to you with the second part of this lesson a little later. To apply